This long insistence on an empty universe, as well as the tinge of superstition attached to reports of falls and fireballs, fueled attempts to find explanations for these phenomena in more familiar terrestrial experiences. One such explanation involved the condensation, often in conjunction with a lightning strike, of minerals within the atmosphere. This idea, bolstered by contemporary enthusiasm for recently discovered electrical phenomena, retained support well into the 19th century. By that time, however, chemical analysis had revealed that the majority of fallen and found stones are both remarkably similar to each other in texture and composition, and markedly distinct from the typical rocks of Earth. This observation pointed to a single external origin for meteorites, and the moon was an obvious candidate. Fanned by several dramatic eruptions of Vesuvius and Etna starting in the 1760s, and followed by alleged observations of lunar eruptions. While the atmospheric and lunar volcanism theories for the origin of meteorites declined, a cosmic origin seemed increasingly possible. In the 1790s, E.E.F. Chladni drew an explicit and unprecedented connection between meteors, fireballs, and native irons, proposing an extraterrestrial origin for these three phenomena, previously considered distinct. He proposed that meteorites were fragments of matter that either had never been consolidated into a planet or had emerged from the violent disruption of a planet by a collision or internal explosion of some kind. Chladni's first report was followed over the next several years by an entirely coincidental spate of highly prominent falls, culminating in the spectacular fall of thousands of stones at L'Aigle, France, in 1803. The widespread publication of these events, including a comprehensive report on the L'Aigle fall completed by Jean-Baptiste Biot on behalf of France's Minister of the Interior, did much to establish that rocks do indeed sometimes fall from the sky. Discovering near-Earth objects. The discovery of Ceres in 1801 provided a new hypothesis for the origins of these rocks, although other, more local explanations retained their currency until about 1860. While conducting observations for what would become a famous star catalogue, Italian astronomer Giuseppe Piazzi discovered a new object, Ceres, in an orbit that appeared more planet-like than comet-like. Ceres also fit what is known as the Titius-Bode law. Published in 1766, this rule inferred from the spacing of the inner planets that there should be a planet between Mars and Jupiter, and another beyond Saturn. The 1781 discovery of Uranus, approximately where the Titius-Bode law had forecast, seemed a confirmation of its accuracy. Ceres, too, was in the right place. Piazzi first thought it might be a comet, but other astronomers doubted that. After the 1802 discovery of Pallas, traveling in a similar orbit, William Herschel declared the two objects to be a new class of celestial body, asteroids. The asteroids occupying orbital space between Mars and Jupiter are known collectively today as main belt asteroids. To mark a distinction between them and the many other varieties of asteroid orbit discovered since, they are still the largest known asteroid population, and one, Ceres itself, was later reclassified as a dwarf planet by vote of the International Astronomical Union in 2006. Main belt asteroid orbits generally keep them far away from Earth, and they are not classed as near-Earth objects. But their orbits can be perturbed, and over the eons, some have been shifted into orbits that take them into the inner solar system. The first such near-Earth asteroid to be discovered was 433 Eros, found in 1898 by German astronomer Gustav Witt. Since the discovery of Eros, scientists and many devoted amateur astronomers have identified many thousands of near-Earth asteroids. But far from the uniformitarian view that extraterrestrial impacts could have no influence on Earth, a very large impact is now blamed for the demise of the dinosaurs, and numerous craters associated with large extraterrestrial impacts have been identified on or under Earth's surface. These impact craters are known as astroblanes, bringing the geological community around to the idea that asteroids and comets have in fact left marks on Earth's surface, was the life's work of Eugene Shoemaker, who also trained the Apollo astronauts in field geology, and whose wife, Carolyn, was one of the most prolific discoverers of comets during the era when film was the discovery medium. The recognition that large impacts could influence the evolution of life itself is an extension of what is known as the Alvarez hypothesis, named for a famous 1980 paper by Luis and Walter Alvarez. This posits that an impact at the end of the Cretaceous period forced the dinosaurs into extinction. Acceptance of the idea that large impacts have transformed both the surface of Earth and life itself represents a rejection of strict uniformitarianism, or what Stephen Jay Gould referred to as substantive uniformitarianism, in a 1965 essay. Three events in close succession brought the potential destructiveness of cosmic impacts to public attention and began moving NEOs into policy salience. The first was the unexpected close flyby of Earth by 1989 FC, discovered after it had already passed by. Discovery of the enormous buried crater left by the end Cretaceous impactor in 1990, or as we will see in Chapter 4, reinterpretation of an already known structure, was the second. The spectacular collision of Comet Shoemaker-Levy 9 with Jupiter in July 1994, witnessed by ground observatories, by the Hubble Space Telescope, and by the Galileo spacecraft en route to Jupiter, was the third and most dramatic event. These led to Congress directing NASA to find at least 90% of the 1 kilometer diameter or larger near-Earth asteroids within 10 years. See Chapter 5. And NASA currently has a directive to discover and track 90% of all the near-Earth asteroids larger than 140 meters. Those about 7 times the size of the Chelyabinsk impactor, which could cause regional damage on Earth in the event of an impact. Once near-Earth objects became objects of policy concern, they also became hazards to be mitigated. The discovery of NEOs and determination of their trajectories was one component of mitigation, but as policy measures started being discussed, other aspects emerged. Deflecting specific threats was one recurrent theme of discussion. Another was civil defense. The first decade of the 21st century witnessed the first impact-related civil defense exercises in the United States, and both NASA and the European Space Agency had plans for deflection demonstration missions to be carried out in the 2020s. At the international level, advocates of planetary defense had established an international asteroid warning network to coordinate observations as well as communications about particular asteroid risks, along with a separate planning group for space-based deflection missions should one be necessary. This also reflects the gradual internationalization of NEO concern. In a recent article, Valerie Olson has argued that asteroids and comets have come to be seen as environmental objects, as distinct from astronomical ones. They are no longer merely intellectual curiosities or research objects for scientists. They are natural hazards like flooding or wildfires and are increasingly treated as risks subject to cost-benefit analysis. As we will see in later chapters, astronomers used this tool of the administrative state as part of their advocacy for NEO discovery surveys and planetary defense efforts. Most near-Earth asteroid discoveries have happened since 1990. In large part, that is due to a technological change in the way astronomers look for them. As we will detail in later chapters, for most of the 20th century, astronomers interested in near-Earth objects, there were not many, had to compare two pieces of film, taken of the same piece of sky but at different times, to find whatever had moved between exposures. It was a painstaking, slow process. During the 1970s, though, Jet Propulsion Laboratory researchers worked to improve charge-coupled detector, CCD, technology for eventual use. in spaceborne cameras. A prototype CCD-based camera was used by James Westphal and James Gunn at Palomar Observatory in 1976. By 1981, University of Arizona astronomer Tom Jarrells was trying to fund a CCD-based telescope dedicated to hunting near-Earth objects at Kitt Peak Observatory. Failing to raise enough money, he and a small team developed the Spacewatch camera, which was attached to an existing 0.9-meter telescope to produce its first electronic images late in 1983. CCDs lent themselves easily to computer-assisted analysis, and by the mid-1990s, other teams were also striving to automate the process of neo-discovery, orbit determinations, and risk-to-Earth assessments. By the 2000s, hundreds of near-Earth objects were being discovered per year with the aid of automation. By the time these words were written in 2019, more than 20,000 were known. And that brings us up to chapter 1. Thank you so much for listening along with me for the introduction to this book. I can't wait to read the rest. You'll have to click on the next video for chapter 1. Take care and be kind.